Hey Tesla fans! Automobile high voltage, welcome to the ultimate hub for everything Tesla. From groundbreaking updates on autopilot and full self-driving, to the latest on Cybertruck, Optimus, Gigafactories, and Elon Musk's bold innovations, we've got it all, right here. If you're passionate about the future of electric vehicles and want to stay ahead of the curve, hit that subscribe button and turn on the bell, because this channel is fully charged with Tesla news, deep dives, and tech breakdowns every week. Let's start our video. Elon Musk has consistently driven Tesla along a visionary path, crafting innovations that stand in sharp contrast to those of competitors like Ford, Rivian, or Toyota. This pioneering spirit, initially forged in electric vehicles, now propels Tesla's ambitious humanoid robot, Optimus, into uncharted territory. Unlike other robotics firms that prioritize rapid locomotion or advanced computational power, Tesla has embraced a distinctive approach, dedicating over half its engineering resources to perfecting the robot's hands. Musk, a leader with unparalleled vision, asserts that the hand is the primary conduit for human intelligence. He contends that, across millions of years of evolutionary refinement, no anatomical feature has been more critical. In humanity's formative stages, our ancestors relied on their hands to construct monumental structures and perform intricate tasks, long before complex cognition emerged. This conviction shapes Tesla's strategy to position hands as the technological cornerstone of Optimus, particularly in its third-generation model, Gen 3. Musk is confident that these hands, empowered by sophisticated engineering and intelligence, will set Optimus apart, establishing it as the world's most advanced humanoid robot, capable of transforming industries and daily life. However, the deployment of such a transformative technology raises profound societal and economic questions, from job displacement to ethical considerations. Today's exploration delves into the far-reaching impacts of Optimus Gen 3's integration into society, with a focus on the pivotal role of its hands. Welcome to Auto Intel. The Optimus Gen 3 hand and forearm, featuring 22 degrees of freedom, has entered early production, demonstrating remarkable capabilities such as catching balls and manipulating delicate objects with finesse. This achievement underscores the hand's centrality to human capability, a truth Tesla seeks to harness in robotics. In a remarkably short period, Optimus has evolved from a conceptual vision to a leader in humanoid robotics. Designing a robot that mirrors human manual dexterity demands extraordinary innovation, with implications that extend beyond technology to the fabric of society. The Gen 3 hand, with its 22 degrees of freedom, doubles the 11 degrees of its predecessor, showcasing Tesla's commitment to practical and societal transformation. The human hand, with its 27 degrees of freedom, enables us to undertake any task within our physical reach, from crafting tools to expressing emotions. Equipped with 5 agile fingers, hundreds of sensory nerves, and a complex mechanical framework, the hand is an unparalleled instrument for creativity, labor, and interaction. Tesla's pursuit of a robotic hand that emulates this versatility positions Optimus as a catalyst for societal change, but its deployment raises critical questions about economic structures and ethical responsibilities. When Musk announced that Optimus Gen 3's hand achieves 22 degrees of freedom, Tesla ignited widespread anticipation, redefining the potential of humanoid robotics. This milestone is not merely about technological prowess but about reshaping how humans work, live, and interact. Advancing from 11 to 22 degrees of freedom, the hand is now just 5 degrees shy of human capability. To provide context, the 11-degree hand already enabled Optimus to fold garments, tend to plants, handle eggs without breaking them, assemble electronic components, transport battery trays, and serve beverages. These feats are only the beginning, as Optimus' manual and cognitive capacities continue to evolve. However, the societal and economic implications of deploying a robot with such capabilities are profound, requiring careful consideration of its impact on labor markets, ethical frameworks, and global economies. Observing Optimus in action, its gait may not immediately captivate. Some liken its movements to those of a cautious elder, noting impacts on balance and fluidity. Yet, when Optimus manipulates objects with its hands, its performance is striking. In recent demonstrations, Optimus has caught a tennis ball with pinpoint accuracy, a task requiring seamless coordination of mechanics and intelligence. The hand's ability to perform such feats stems from its advanced design, which accounts for nearly half the robot's mechanical complexity. In humans, each finger comprises 3 joints and a sophisticated muscular network. Reproducing this in a robotic hand, while maintaining a human-like scale, is a monumental achievement. Tesla's Gen 3 hand, with its 22 degrees of freedom, surpasses other commercial humanoid robots, most of which operate with only 5 or 6. Each finger moves independently, capable of rotation, flexion, twisting, and delicate contact, enabling tasks like typing or dishwashing. These capabilities underpin Optimus' potential to transform industries and households, but they also introduce significant societal challenges. One of the most pressing concerns is job displacement. Optimus Gen 3's hands enable it to perform a wide range of tasks traditionally done by humans, from factory assembly to domestic chores. In industrial settings, the robot can handle minute components, secure screws, apply adhesives, and inspect products, tasks that currently employ millions of workers. Its ability to work tirelessly, with precision and adaptability, could reduce the need for human labor in manufacturing, logistics, and warehousing. In households, Optimus can perform chores like laundry, cooking, cleaning, and gardening, potentially diminishing demand for domestic workers, such as cleaners or caregivers. While this could enhance efficiency and reduce costs for businesses and households, it risks displacing workers, particularly in low-skill sectors, where retraining opportunities may be limited. The economic ripple effects of such displacement could be significant, potentially increasing income inequality and straining social safety nets. However, Optimus also presents opportunities for economic transformation. By automating repetitive or hazardous tasks, the robot can free human workers to pursue more creative, strategic, or interpersonal roles. In factories, Optimus could handle dangerous tasks, such as working with heavy machinery or toxic materials, improving workplace safety. In homes, it could alleviate time-consuming chores, allowing individuals to focus on education, entrepreneurship, or leisure. The hand's dexterity enables Optimus to take on roles that require precision, such as assembling electronics or assisting in medical procedures, potentially creating new industries and job categories. For example, the deployment of Optimus in eldercare could lead to specialized roles in robot-assisted caregiving, blending technical and human skills. The economic benefits of increased productivity could drive growth, provided societies invest in retraining programs and education to prepare workers for a robotics-driven economy. Ethical considerations are equally critical. The hand's ability to perform gentle gestures, such as shaking hands or offering a comforting touch, makes Optimus a potential companion in elder care, hospitals, or educational settings. Its tactile sensors ensure safe, calibrated contact, fostering emotional connections that are vital in these environments. However, the integration of robots into sensitive human interactions raises questions about dependency, privacy, and emotional authenticity. For instance, relying on Optimus for caregiving could reduce human contact for vulnerable populations, potentially leading to isolation. The robot's AI, which monitors hand movements and adjusts force dynamically, must be rigorously tested to prevent errors that could cause harm, particularly in medical or caregiving contexts. Ensuring that Optimus respects user privacy, especially in homes where it may access personal spaces, is another ethical imperative, requiring robust data security measures. The societal acceptance of Optimus depends on addressing these concerns transparently, ensuring the robot enhances rather than undermines human well-being. The global deployment of Optimus Gen 3 could also reshape economic dynamics between nations. Countries that adopt the robot early may gain a competitive edge in manufacturing and services, boosting productivity and innovation. However, the high initial cost of Optimus, estimated at around $40,000 due to complex components like rare earth magnets and servo motors, could limit access in developing economies, exacerbating global inequalities. The reliance on specialized materials, subject to supply chain constraints, further complicates equitable distribution. Tesla's long-term price target of $30,000 aims to make Optimus more accessible, but achieving this will require significant advancements in production efficiency, which may take years. In the interim, wealthier nations and corporations are likely to benefit most, potentially widening economic disparities. The hand's role in these impacts is central, as its dexterity enables Optimus to perform tasks that drive economic value, from industrial precision to domestic convenience. The biomimetic design, with elastic cables mimicking human tendons, allows the hand to be lightweight, precise, and energy efficient, supporting a wide range of applications. The tactile sensors, which perceive textures, pressures, and temperatures, enhance the hand's versatility, making it suitable for tasks like cooking, caregiving, or quality control. However, the complexity of this design introduces production challenges, such as sourcing magnets and calibrating sensors, which could delay widespread adoption and limit societal benefits. Ethical frameworks must also address the potential for misuse. While Tesla has implemented safety features, such as automatic shutdown for risky behavior and role-based controls to prevent harmful uses, ensuring these systems are infallible is critical. The hand's strength, capable of lifting heavy objects or performing precise manipulations, could be exploited if not properly regulated, raising concerns about safety in public spaces. Public perception of Optimus will play a significant role in its societal impact. The robot's human-like hands, capable of expressive gestures, may foster acceptance by making interactions feel natural. However, fears of job loss or dehumanization could spark resistance, necessitating proactive engagement with communities to highlight Optimus benefits, such as enhancing productivity and safety. Education campaigns and pilot programs, such as deploying Optimus in factories or care facilities, could build trust, demonstrating its value while addressing concerns about displacement or ethics. Tesla's mission to bridge virtual and physical AI through Optimus Gen 3 hinges on navigating these societal and economic challenges. The hand, as the primary interface between digital intelligence and the physical world, is at the heart of this transformation. While Optimus holds the potential to redefine labor, enhance human well-being, and drive economic growth, its deployment must be managed with foresight to mitigate risks and maximize benefits. What are your thoughts on the societal and economic impacts of Optimus Gen 3? Share them below. Thank you for joining us, and we look forward to your next visit.